We want to talk about linear expansivity, that is thermal expansivity in physics. Like thermal expansivity simply means the application of heat that causes expansion. Thermal means heat, and the expansivity means expansion, something that will expand. So it means that when you have an object of original length, that is something that you know that this is the size of this thing, then you apply heat, or you put it in the fire, you will see that that metal will increase in size. So that is what is called expansivity. And expansivity, we talk about linear expansivity. Linear means in a straight line, in a straight form. So there are what is called linear expansivity, area expansivity, and volumetric or cubic expansivity. But we're going to talk about linear expansivity, which involves increase in length of a substance per unit length, per degree rise in temperature. So you can see that every degree rise in temperature, that the length of a material must definitely increase, or will definitely increase. So that is why we are having this linear expansivity. So we can see some of the problems we need to solve in this linear expansivity. We have, for example, we have a brass rod is the morning is 2 meter long at a certain temperature. What is its length for a temperature rise of 100 K, which is Kelvin? That K is Kelvin. If the expansivity of brass is 8 times 10 raised to power of minus 6 per Kelvin. So you can see that we have so many of them. I'm going to deliberate on these examples. You see very well that here, this is the formula for linear expansivity. This is linear expansivity symbol, the symbol for linear expansivity, and which is equals to length, that is the final length, minus the initial length. The final length is the length that is the increase in length. For example, if you have a rod of 2 meters, so when you put that rod in fire, the rod will increase to 3 meters. So the first one is the initial length, which is the L1, which is the first length, which is assuming to be 2 meters. Then when you put it in the fire, it becomes 3 meters. So the 3 meter will be the final length, which is the L2. So L1 all over L1, which is also the initial length. Then theta 2 is the last temperature, which made the body to expand. While the initial temperature is the temperature of the body when you have not added it in water, sorry, in the hot fire. So that is why the first temperature that the body possesses is known as the initial temperature. Then the final temperature is the temperature when the body is heated and the expansion takes place. So that is why we have theta 2 minus theta 1, just like we have in L2 minus L1. So L1 is the initial length at theta 1, which is also the initial temperature at that temperature, and L2 is the final length at theta 2, which is the final temperature. So this alpha you are seeing here is the linear expansivity. So this is the formula. So you can use this formula to solve any of these problems. You can also use this formula to find the change in length. So you also, for example, you can also define this linear expansivity in this way. You can also define it in this way. The linear expansivity can also mean it can also be change in length all over original length multiplied by theta 2 minus theta 1. So you can also call it like this: theta 2 minus theta 1 is equals to theta, which is something as change in length all over length 1 bracket change in temperature. So each of these formula can also go. So each of these formulas, you can see that theta 2 minus theta 1 is equal to theta, which can also be change in length. Change in length means L2. This change in length means L2 minus L1 all over L1 bracket. This change in theta means theta 2. Change in length means change in length. This data you are seeing is called data. It is called data. This data you are seeing here means change in length. So change in length means L2 minus L1, and change which all over L1 bracket. Change in theta means theta 2 minus theta 1. So this is how to solve linear expansivity. This is the formula. So let's see how we can solve this problem. Definitely we arrive to a very successful outcome. Thank you.